And yeah.
It's 6 o'clock.
Hi everyone, can you hear me? I guess. Yeah. Okay, great. So, out of all of the hobbies I could have chosen, I chose something that requires me to be out in the middle of the night with mosquitoes and stray dogs and a whole bunch of other things. But there it is. So let me walk you through my experience in the journey I've taken in deep sky photography. This might be a little technical, but I'll try and keep it just top line. So you can't get into astronomy and photography without getting a little technical, but we'll see how it goes. So deep sky astrophotography is a combination of astronomy and photography, and I'll be covering a little bit about the night sky, the equipment that's used, some of the workflows, sample images that I've taken will be, inserted in the presentation, and I'll talk a little bit about upgrades. This is a famous picture, as you probably have seen in the past, from the Hubble Space Telescope. It's in the Eagle Nebula, we call the Pillars of Creation. So there are two types of astrophotography, what's considered deep sky and nightscape. Most of us are familiar with nightscape photography, which is fairly large portions of the sky, Milky Way, star trails, northern lights, and does include some terrestrial foreground. Whereas deep sky astrophotography are, very small, faint objects like planets, galaxies, nebulae, clusters, and comets. You require specialized equipment for deep sky astrophotography and long lenses and exposures in hours compared to exposures in seconds with nightscape photography. So let's talk a little bit about the night sky. You need to know really about DSOs, or deep sky objects, their size, what wavelengths of light they emit, so you can capture that on your sensor. The visual magnitude is the brightness of these objects, where they're located and how they move through the sky, and some imaging obstacles, such as seeing, which are environmental factors, and light pollution. There are many different types of deep sky objects. Reflection nebula are essentially gas clouds around stars, and the starlight highlights the gas clouds. Emission nebula are where the gas clouds are actually ionized and emit radiation, which you see. We're all familiar with galaxies. Globular clusters are clusters of stars which are held together by their own gravity. They don't spin around, they just, huddle together. Planetary nebula are gas clouds that were emitted when a star in the middle exploded. And so you're seeing the gases emitted by that star. And we're all familiar with comets. Nebula emit radiation in specific wavelengths. For example, the Carina Nebula, the biggest wavelength is hydrogen alpha. There's some sulfur, helium, and oxygen. Whereas galaxies typically emit a broad band of radiation. So it's very important, if you're photographing nebula, to know where they emit radiation so you can focus on that and eliminate everything else. The other important thing to understand is the coordinate systems of the sky. There are two main coordinate systems. One's called the alt-az, or altitude azimuth system, which is essentially how high a star is above the horizon, gives you the altitude, and how far over it is from the northern meridian gives you the azimuth. The RA-DEX system, or equatorial system, really is this system tilted towards the rotation of the axis of the Earth. and it's right ascension and declination. Another important factor is to determine where north is, the rotation of the Earth. In the northern hemisphere, it's pretty easy because Polaris, the North Pole star, is very close to it, although not exactly at it. Whereas in the southern hemisphere, there's no real object at the South Pole. You have to triangulate it from Octans, which is a constellation. So the primary equipment that we use in astrophotography is a mount or tracker. It tracks the sky. A lens or telescope, which creates the image. A camera, which records the image. A controller, which coordinates the shoot of the mount, lens, and camera. And then eventually a computer to process the images that you capture. So my approach has been, as I got into this, use standard photographic equipment where possible, and then add on specific equipment as needed. So there are two types of mounts, the Altaz and the Equatorial. The Altaz mounts are usually used for observing. They're simpler setups, more portable, and are cheaper. And this is one of them. You have a vertical axis for the azimuth and a horizontal axis for the altitude. The equatorial mounts are usually used for imaging or photographing. They are much more accurate, and you can put heavier payloads of telescope and camera and other equipment on them. And here you can see the two axes are not vertical, but are pointing towards the North Pole. Why is Equatorial better than Altaz? You can see the impact of image rotation. With an Altaz system, even though the object that you're viewing is rotating around with the rotation of the Earth, your frame is always vertical. So when you try to take multiple images and stack them, you wind up losing the periphery of your image because all of these are misaligned from each other. Whereas with the equatorial system, your frame rotates with the object. So when you stack all of these, they wind up stacking perfectly, and you don't lose any field of view. Yeah. Maybe about a year and a half, something like that. Yeah. So here are some equatorial mounts. They come in three classes: portable class, an intermediate, and a heavy duty. The portable, essentially, your payload is about 10 pounds, less than 10 pounds. So camera, tripod, camera, ball head, and lens need to be less than that, and they run in this price range. The portables, now you're actually using a telescope. They can go up to 30 pounds, and from 30 and above, you get the heavy duty ones, which are very expensive. I use this middle one here, which is in the portable range, because I wanted to be able to use it not only in my backyard, but travel with it or go to a dark site if needed. So here's my equipment. This is standard photographic equipment: a tripod, ball head, my camera, intervalometer, and a couple of lenses. And then I added some of these elements. The mount, which is this piece here, a polar scope to align the mount with the Polaris, a power cell to drive the mount, filters to suppress light pollution, a heater to handle dew accumulation on the equipment, and a button-off mask to help in focusing, and I'll talk about that in a little bit. So all of these items cost about $1,500. Here's the demonstration of the accuracy of this mount. I did a 4-minute exposure, and I focused on Polaris in both cases. And I turn the mount off. You can start seeing in 4 minutes, you can start seeing the stars streaking And I sort of amplified it here to show you that. But with 4 minutes with the tracker on, you're getting no streaking, you're getting pinpoint stars. So that tells you that the tracker is actually tracking the stars. The tracker has 4 tracking modes: tracks the sun, tracks the moon, sidereal is tracking the stars, and half sidereal, which is half the speed of tracking the stars. And why would we want half a rate, sidereal rate? If you take a picture at sidereal rate of a comet, the stars and the comet are in focus, but the foreground is out of focus. But if you go to half that rate, somewhere in between, the stars stay in focus, and now your foreground is also in focus. So that's when you would use half sidereal rate, when you have some foreground. So what are the key challenges in DSO photography? You're imaging dim objects, so you need to maximize the light collected, use a long focal length to magnify the image, and long exposures. You want to boost the signal, so you have to minimize light pollution, get a sensor with high sensitivity, and use wavelength filters so that you cut out everything else that's not important to you, and only those wavelengths that the object is emitting. You need to minimize noise, and we all know that that means a low ISO. You cool your sensor, and I'll talk a little bit about that coming up. And you take multiple images and stack them. And since noise is random, adding up all of these images will cancel out some of that noise. And to get pinpoint stars, you need to use a tracker, otherwise you'll get streaking. Accurate focus, and eliminate aberrations coming in from lenses, etc. So here's what, getting into this, you would say, okay, I expect to be able to get good images, but when you take a single image, you can barely see the nebula. Even after an hour of exposure, it's not much improved. It's only when you suppress the noise and post-process that you get the famous Heart and Soul Nebula. So for a successful outcome, you need to plan your shoot. You need to align the mount to the North Pole. You need to be able to focus at night, which is not trivial. You need to manage light pollution and master the art of processing your images. I'll go through some of these. Where and when to shoot. There are some apps that help you. Light pollution map tells you how much pollution you have where you are planning on shooting from. That's my backyard, so I'm in a pretty hot zone, a lot of light pollution. But if I went to the Okefenokee swamp, that would help. There's another app called Clear Outside, which tells you cloud cover, visibility and fog, wind, and dew. So this helps you plan which night you're going to be shooting in. It also tells you when sunset will occur and what phase of the moon you're in, because moonlight also hurts. There's a seasonal viewing in astrophotography. Typically in the spring, you shoot galaxies. The summertime is good for the Milky Way core. Fall, you get some other galaxies and nebulae, and the winter is the best time to shoot nebulae. What to image? There are many targets that we can image. They fall into nebula, clusters, and galaxies. And all of them are categorized in catalogs with a number, and they have a visual magnitude, which is how bright are they. The brightest is the sun at -24, and the dimmest is what Hubble will see with 18 hours of exposure. And that's a +30. So most of the objects that I've been working with are in this range here. And there are two apps, Starwalk and Stellarium, that tell you where to find these objects and how they'll move through the sky. How much to capture? Depending on your lens, sensor, etc., your frame will include little or more of the sky. So telescopius.com allows you to input the object that you're shooting for, your focal length of the lens, your sensor size, and it'll frame out exactly how much you expect to get. So if you want to get to focus on this area, it'll tell you, you can change your focal length and it'll show you how much you're going to actually get. Here's an example of Orion. If you take a focal length of 35 millimeters, you can calculate, you can capture the entire constellation. But if you only want to capture the belt, you have to go to 105 focal length. But and if you only want to capture the nebula, you have to go to 600 millimeters focal length. And this is what I captured at 600. Orion is 1,300 light years away. This is Orion Nebula, and that's the Running Man Nebula. Can you see the Running Man in it? Yeah. Here's another image I captured of the Veil Nebula. There used to be a star somewhere here, and it exploded, and that's the gaseous cloud of that's remnant. That's about 2,400 light years away. And this is a chain of galaxies, Markarian chain, and these are all individual galaxies about 50 million light years away in the constellation Virgo. Polar alignment. This is very critical because the more precisely you can get the polar alignment, the more closely you'll track the stars. So you can use a reticule, look through it, and it'll tell you where to put Polaris. Make sure you put Polaris in there and you'll be aligned. And this is mostly a rough alignment. This is a better alignment, the Pole Master, which allows you to rotate your mount and then tells you where exactly the rotation of the Earth is centered and in relation to Polaris, and you can align it to that point. But suppose you can't see Polaris because it's blocked by a building or a tree or whatever. This app will allow you to take a picture of any part of the sky, and based on where the stars are located in that picture, will know where you're pointing, and then will tell you how many degrees to move over to get to polar alignment. And that's called plate solving. Oops. I think I must have hit something. Okay. These are two galaxies, Bode and Cigar galaxies, about 12 million light years away. And this is a Whirlpool Galaxy. It's about 31 million light years away. And this big galaxy is eating this little galaxy. They're so close to each other that someday they say that Andromeda Galaxy is going to devour the Milky Way. I'm hoping I'm not wrong for that. So some factors that prevent us from getting pinpoint stars. We all know about color fringing. This is essentially a problem with most lenses. You have to use special glass and designs to be able to solve those problems and get no color fringing. And this is an example of color fringing, chromatic aberration. You can see the separation of the colors. Poor focus. These aberrations, all of which are resident in lenses, but reducing the aperture allows you to minimize them. Star trails, we've talked about getting a good mount and aligning it properly. And field curvature. This is not an issue with camera lenses. It's mostly an issue with telescopes. And the curvature of the field is such that if you try to focus in the middle, the outside, the periphery will be out of focus. Or if you try to focus in the periphery, the center will be out of focus. And you need a field flattener in the optical train to be able to eliminate that. Here's a shot of the Pleiades, or the Seven Sisters, about 400 light years away. This is what a Bartonov mask is to help focusing. It's essentially a disk with this pattern etched into it, and you put it over your lens, and you point at a star, and you get these pictures. The stars here, if in the middle picture, these spikes go right through the star, you're in perfect focus. If one of the spikes is left of the star, you're inside focus, or conversely, you're outside focus. So you can tweak your focus so that all the spikes cross exactly at the star. Light pollution. This is another challenge. There's a bottle scale, and no, this is not the ex-quarterback of the Jaguars. It's a scale from 1 to 9, where 9 is inner city sky, where you can't see anything because there's so much light pollution. And 1 is an excellent dark side. And somewhere in here is where we are, suburban skies, where you can see something. Most of the culprits are high pressure sodium vapor lamps and LED lights. And this is what they look like. If you compare them with what the nebula is emitting, it lays right on top of this. So you've got to cancel these out without impacting this. And that's the challenge. So how do you do this? You shoot away from city lights, might help a little bit, or towards the zenith. Use light pollution filters, or travel to a dark side. Now here's a Canon 5D sensor. What has happened with these, with most camera lenses, is that they put in a IR cut filter in the infrared range to help with daytime photography. But where your hydrogen and sulfur peaks are, is where the sensor is very weak in sensitivity. So it's only about 20%, 10 or 20%. So these filters this is a broadband filter, tends to block out some of the ranges. This filter, which is the one that I use, ultra high contrast filter, allows these bands and those bands to come through and blocks everything else. And then there's the extreme, which is line filters, where you go in and take 4 shots with different filters, 1 for each of these wavelengths. That's 4 times is too much for me to be out there. The filter that I use is a clip filter, Astronomic UHC, and it really fits into the front of the sensor. So it actually just clips in, you don't put it on the lens, right in front of the sensor, looks like that. And now you can clip on any lens, you can mount any lens you want, and the filter will work with that lens. And it eliminates, it only allows hydrogen alpha, oxygen, sulfur, and helium to go through. So here's what it looks like. Without any filter, it's pretty washed out. There's maybe a hint of a nebula here, but you do the same conditions with the filter, and you can start seeing the nebula. Now you take many of these images, post-process it, and you get the Rosette Nebula. In Monoceros, the constellation Monoceros, which I found out in Greek means unicorn, and it's 5,000 light years away. So here's my workflow. I plan my shoot, set up the equipment, align to the pole, establish where the DSO is that I want to shoot, and establish focus, shoot my frames, stack the frames, and then go into Photoshop and archive. So that's my workflow.
Which stacker do you use?
There are two stackers that I use. Here's the camera. I shoot both in RAW and JPEG so that I can look at the JPEG pictures, images, and see what I've got. But I process all my images with the RAW files. I use this ISO range, 400 to 3200, auto white balance, because I can always correct that in post, and shoot manual. I use two lenses, one for narrow field and the other for wide field. So now what do I shoot? A few trial frames, really short exposures to locate and frame the DSO. The lights are the actual images that I'm going to wind up with, and I shoot them at a low ISO, 2-minute exposure, and 1 to 2 hours worth of total exposure. Then I have to shoot dark images where I put a lens cap on the front and shoot the same ISO and exposure time. This is to measure and eliminate heat and pixel noise from the sensor. Then I shoot bias frames, which is at the fastest shutter setting of the camera. And that's to eliminate electronic noise from the sensor and the camera. So what I would then do is take these lights and subtract out the darks and the biases. And that's all done in software. So the stacking software I use is Deep Sky Stacker or Sequitur. I try them both and see which one works better and use that. Then I've got a process which involves star removal and a whole bunch of plugins to Photoshop to process the image. And I'll sort of walk you through a top line process for doing that. So here's an example. Gamma Cygnus is the region I'm looking at. I take a single 2-minute exposure and that's what it looks like. If I stack 40 of them to get 80-minute total exposure, you can start seeing the nebulosity coming through. And then when you stretch it in Photoshop, you really start seeing some better image. But this is not as good as it can get. And stretching it some more will only blow out these stars and overexpose them. So I go through a different process. I start out with a stretched image. I put it into StarNet and subtract out the stars and the nebulosity. So they're in two different images. This is a stars only image, and this is a nebulosity only image. And I take this image and increase the luminosity of the nebula, and then add back the stars for my final image. So that's the process that I go through. An example of that is the North America Nebula. Can you recognize the North America or the US shape in this nebula? So it's in over 2,000 light years away in Cygnus. This is the Lagoon and Trifid nebulas in Sagittarius, about 4,000 light years away. So there are decisions that I've had to make along the way, and I'll just go quickly over these. System robustness versus portability. I talked to you about that, and portability is what I've chosen. I've chosen to manage light pollution because I'm shooting in my backyard, essentially. I've gone to more of a manual setup, but I'm migrating to automated. I'm using flexible equipment. Most of my camera lenses, etc., are standard photographic lenses. But I could get dedicated telescopes and cameras, etc., but that would be a next step. This is an interesting one. Half the community prefers to be realistic in their rendering. There is nothing that's not there is going to be added, and nothing that is there is going to be taken away. So they want it to be realistic. But others want it to be more artistic, and they go to false color images, etc., and add in things to make because they're being artistic about it. And then, of course, the big dollar figure, how much to invest in and when. Okay, so for mounts, you can graduate to larger mounts, go to guiding the mount. So rather than just having a mount which moves with the sky, you actually actively guide it by watching a star. Let it correct itself if it goes astray. Have a go-to capability, which is this handheld controller, where you plug in Orion M42, and the mount will automatically go to Orion, and you can start shooting. You don't have to go and hunt for these things. And Wi-Fi control, this is so that you can operate the entire setup from your home rather than outside. And this is especially good for northern winters, where you can sit in your den and control your telescope with Wi-Fi. In terms of going to upgrading from a camera lens to a telescope, there are refractors, reflectors, and catadioptric. Refractors are what our current lenses are. Essentially, the light comes in here and is refracted and goes through to an eyepiece or camera that's out here. Reflectors, the light comes in here, is reflected back, and then goes out the side, and your camera is up in here. And catadioptrics are where the light is folded in three times, and your camera is out here. These are best for long focal lengths. These are good for visual, and these are good for short focal lengths. The last area to upgrade is the camera. I'm using a mirrorless camera right now, or a DSLR, but it can be modified. You can take out that cut filter, UV and IR cut filter, but then that means the camera is no good for daytime photography, and it voids the warranty of the camera. Or you can get a dedicated astro camera, which is one of these, one-shot color or mono. There's cooling in these, which cools it to 35 Celsius below ambient. So if you're sitting in at 35 degree, it'll cool it down to 0. And what that does is it eliminates the noise of this in the sensor completely. Here's an example of modifying a DSLR. As I told you, this is an icon. It has a cut filter, so unmodified, it looks like this. You take the cut filter out and you get back your sensitivity of the sensor. What does that look like? This is a stock shot of Orion, Orion's belt. And if you modify the filter or the sensor, you get a lot more nebulosity. The difference between a DSLR and a cooled camera, this is the Helix Nebula. You can see how much more dramatic data you can capture, and it really jumps out at you. And if you look down here, this took 2.7 hours of exposure to get. This took about an hour and a half. So you get much more for less time. Here's the artistic rendering of the Rosette Nebula. You can do monochrome, you can assign it all to the red channel, or you can get false color images. This is the Hubble Space Telescope. Its palette. You can, depending on the filters you use and the channels, the color channels that you assign to, you can get different color effects. So this is what the system would look like. This is my system today. It would look like this. You'd have a primary imaging telescope with its camera. You'd have a guide scope with its camera, and then you'd have a beefed up mount. So what do you expect? What should I expect to get in terms of image improvement if I went down to this? Here's the Whirlpool Nebula that I shot, that's what I would expect to get if I went to the next step. Or here's a Rosette. A lot more detail, a lot more clarity, a lot more expense. So, on my experience, be prepared to lose a lot of sleep. Chris will attest to that. And for at least 2 hours, you want none of this stuff coming in your way. No moon, no clouds, no wind, no cars, no airplanes, definitely no pets or stray animals hitting your tripod. Most of these nebula are invisible to the naked eye, so you wind up hunting for them quite a bit. Therefore, you may need to shoot the same object many times, either because you didn't quite get it centered or you want to increase the exposure time. And it's a process. But when it all comes together, it makes the effort worthwhile. So here's an example of the Horsehead Nebula, and that's the Horsehead right there. This is in Orion, 1,300 light years away. This is an explosion of a star called the Crescent Nebula, about 5,000 light years away. And that's the Andromeda Galaxy. Thank you.
Anybody that's on
Pardon? The closest one, I haven't gone there, is the Okefenokee. But you know, to take your equipment out there, I haven't been, you know, I haven't shot there. All of this work has been done in my, you know, on my driveway.
And your view, if somebody asks a question,
Okay.
Edgar, you decided to upgrade to the more expensive equipment?
Well, it slowly. I've got myself a new mount, and I'm still working with it, aligning it up, etc., getting familiar with it. But to go to a telescope, that is going to be quite a challenge, because these things are heavy, and you know, it won't be portable anymore, and they're pretty finicky telescopes. Oh, sure. Go.
Sorry. Were you a photographer before you chose to focus on stars?
Well, the question is, was I a photographer before I chose to go into this field? I would say I was an amateur photographer. You know, belonged to the photo club and went on a few trips, but I had to learn this field from scratch, pretty much.
And did you teach yourself?
Yes.
Wow. Beautiful. And what made you go into this field? Why do you think you would?
Well, the question was, why did I go into this field, and what made me go into it? I think it was my technical background. So I have a degree in physics and strong in math. So and I used to design lenses during my career. So it sort of fit. It's a very technical field, even though the results are very you know, artistic. The field is technical, and that's what attracted me. It's not for everyone, I'm sure.
You
Yeah.
said you shot most of these from your driveway?
Yeah. I live in Queens Harbor, which is right across the ditch.
So aren't there what, I mean, I live in Del Webb, but it's with the lights on.
Yeah, so the question is, you know, how do you do it with lights on? Queens Harbor recently converted to LED lights, and that was just a killer. They used to have high pressure sodium lamps before, and there are filters that can manage that. But LED lights are so broadband that it's very difficult to manage it. So, you know, I use filters to try and minimize the light pollution. Question, would the calibration process normal? I didn't see that.
Question was, would the calibration process, normal dark bias frames, be helpful for night sky photography, or is it worth the trouble?
For nightscape photography, it's probably not worth the trouble because the exposures are fairly short. The problem with deep sky photography is that the exposures are so long that the sensor gets heated up and all the electronics in the camera get heated up, and that creates electronic noise. So you got to subtract out that noise, hot pixels and electronic noise. The exposures in nightscape photography are, 20 seconds, 30 seconds. That's not going to be an issue.
Did you get the A7 specifically for deep space optics?
No, I had that before for my regular photography, and I've just used it for deep sky photography.
And what does the full setup cost from Crescent, etc.?
The full setup from
Glasses.
Crestron. I don't know, Crestron.
Sean,
I'm not
what's
sure.
that Crescent?
Maybe, Edgar, maybe it's not Crestron, but
Celestron, but not Crestron.
Celestron, yeah, Celestron.
Celestron, yeah. That's a telescope manufacturer. It depends on what level you want. If you want a mount, telescope, and camera, it'll probably run you $3,000 to $4,000. Yeah.
Edgar, are there expert groups that you have gone to help you with your knowledge? Is there a group out there, audio groups out there that you rely on?
So the question was, are there expert groups that I can go to help me with the knowledge and that I can rely on? It's mostly internet-based. Astro Backyard is a Canadian amateur who posts a lot of videos teaching about astrophotography, and he shoots from his backyard and goes through all of the trials and tribulations and sells courses and YouTube videos. So that's one example. I've had a couple of pictures in the presentation from some of these people that I've used to learn. But in essence, it's just, internet based. I haven't gone to any classes or. Oh, there's another one here.
We tried the best plugin to use an Infinity photo.
No, just from astronomy tools. I haven't tried.
Anybody else have any questions, either in here or online?
Yes.
Yeah, Infinity Photo just added a whole big deep
Oh,
sky
yeah.
with their newest upgrade.
Yeah. I think the comment was that Affinity Photo has added a whole suite on the latest upgrade. That may be, I use plugins for Photoshop so that I can stay in one platform, and I think I listed some of them out, and You just use them as you need them. Not for every picture, but for wherever they need it.
Shoot at minimum humidity.
No. That's too tough in Florida. But you want to make sure that if your humidity is too high, your equipment, especially your lens, is going to start fogging up. So you need to have a lens heater to counteract that, and that's what I use.
Even in Florida.
Mostly in the winter time, when the humidity runs up and the temperature is low. Yeah. Yeah. In the summertime, it's not really an issue, but as you get to the fall and winter, yeah, I've had, and sometimes if you forget to put it on, you might go for an hour shooting and then find out all of your images are ruined because you had fog on your lens. So that's happened to me. So Jim, you can come by anytime and any night and see me. Yeah. It is.
The comment was, it's boring.
Yeah. Yes.
Do you sell your images? Do you promote your images?
The question was, do I sell my images or promote them? No.
Just for fun.
And I haven't printed an image yet. So,
I expect you also.
no.
So I want to thank the printer, I want to thank Edgar for his patience in putting this presentation together a year ago.
All right.
And we kept rescheduling it to get it to where we would be face to face. I really
Right.
appreciate your patience.
You're welcome. Thanks.
All right, so we do not need to put the chairs up. They're going to go ahead and do that for us. So put them out. But I guess we don't push on over there. It's the rest of all that. All right, thanks everybody. Oh, yes, please. I have this tonight, everybody. You're not sick. Go ahead and introduce yourself.
My name is Rosette. I'm on the
What did you say? We have a presentation, just for a second.
My name is Teresa, and I've been here in Atlanta for probably three years. And I love to take pictures, so I decided that and yeah, I'm glad to be
Welcome.
Okay. All right. So you post that up on the website or whatever? Yep. Okay, great.